before we look at the code for our next algorithm, let's show how it works in our example. So here's the same example we just looked at for our first implementation. We're going to again begin by adding v1 to our minimum spanning tree. But what we're going to do now is we're going to store some information. At every single vertex, we're going to store the cost of getting to that vertex, the best we've found so far. So if we look up here, we're going to store a cost of 2 up here and a cost of 3 down here. For every other vertex, the ones we haven't found yet, adding them would cost infinitely much because we have no way of getting there. So let's add infinities for all of those. And now what we're going to do is look over every single vertex not in the graph, and we're going to find the minimum number between those. That is a much easier problem, it seems like. I just look at those and go, 2 is the best. So let's add 2 to the graph. So we add 2, we shade it, and now we're going to look at every single edge incident on vertex v2 and update sizes accordingly. So we have 3 edges. v1 we don't need to consider because it is already in the minimum spanning tree. 5 is less than infinity the last time I checked, but I'm not too good at math. So we're going to update that infinity to be 5. And for the sake of the algorithm, what we're going to do is we're going to keep track of the fact that the way that we got that 5 was from v2. So we remember that somewhere. And now let's update v3. 7 is also less than infinity. And we're going to remember how we found that 7. And now we look at our values. We have 2, 7, 5, and 3. 3 is the winner between all of those. So we go from v1 to v6 and add it to the minimum spanning tree. And now we look at every edge incident on v6 and update the costs. So we update 5 to be 4 because 4 is less than 5. And then we say we have a new parent. Let's just get rid of the old one. If you wanted to, you could leave this in and try to exit out, but it gets really messy to do that, so I'm just going to get rid of it. But if you wanted to show all of the work, maybe you would include it, and don't really care too much. Now, let us look at the remaining edges. We still have this edge down here. 1 is less than infinity, so we are going to update that cost to be 1, and then update the way we get there as such. And now, we look at all of the vertices. We have 2, 7, 4, 1, infinity, infinity, infinity. 1 is the winner between all of those. So we connect v6 to v7, shade v7 accordingly because we've now added it, then check every edge incident on v7. Looking at this edge here, 3 is less than 4, so we update that cost again. And then we have 3. And now we update the cost of v8. It is now going to be 4. And now we choose the parentage according to what we just did. And then we look at all of the vertices. We have 2, 7, 3, 1, 4. Sorry, this 2 we don't really care about anymore. But we have 7, 3, 4 for the white vertices. Sorry about the confusion there. The winner between 7, 3, and 4 is 3. So we're going to add 3. And how do we add it? We add it via that gray pointing arrow. And maybe we should have deleted this one like we did before. And then we add v4. And then we look at every edge incident on v4. That connects it to a blue node, to a blue node, to a white node. So we update the cost for v5 to be 5. And we say, how do we get there? We got there from v4. And now we look at all of the white vertices. We have 7, 5, 4, infinity. 4 is the winner there. So we add v8 to the graph, and then we color it. Then we look at every edge incident on v8. 6 is not less than 5, but 9 is less than infinity, so we're going to add v9, and we're going to replace it with 9. And then we have a temporary parent there pointing down. Now we look at our edges. We have 7, we have 5, and we have 9. The winner between them is 5. So we add v5 to the graph, and then we color it accordingly. And now we look at every edge incident on V5 that connects it to a white vertex. This one has a weight of 9. That one's not cheaper. This one has an edge of 8. That is cheaper. So we update 9 to be 8. We get rid of the previous parent, and we update the parentage to point back at V5. And now we compare 7 and 8. 7 is the winner. So we connect there. And we color it. And now we check every edge incident on V3. There's only one that's of interest. That's this edge here. And we then update the cost of this vertex to be 6. And then we connect the final vertices and shade accordingly. So we again have a minimum spanning tree. It's the exact same one we found before, but now we have only had to check the vertices. We didn't have to check the edges, and that will make us some serious gains in terms of the runtime. Let's see how the code looks here. We begin by defining U to be the set of all vertices. We then assign a cost to every vertex except the starting vertex to be infinity, and the starting vertex has a cost of 0, and it has no parent. Now, what do? We do the exact same sort of thing we did before. While we are not empty, and there are nodes to find, so something that does not have infinite cost, we're going to find the minimum node. So we first find the minimum cost node in U, and then we remove it from U and add it to the tree. So this code here makes the greedy decision, makes greedy decision. And then the code below, all of this code, let's highlight that in a different color. All of this code down here that I'm going to highlight in lavender. All of that code, what it's doing is updating costs. So let us try and analyze this algorithm then. If we look at this step here is now a lot easier. Let's begin by maybe highlighting that in a third color here. Let's do this green. We haven't used a green yet. We're going to have to analyze all these different bits. At the top, this code's not too bad to analyze up here. This code here, that just loops over every vertex. So this takes Cn time, where n is the number of vertices. Then everything else is basic assignments, nothing fancy there. Again, this loop, the entire loop, runs n times. And let us examine the cost of the different components there. In order to determine the minimum cost vertex, what we're going to do is loop through every single vertex in U. So let's try and analyze. At line 9, the number of vertices in U is, well, on the first run, U had every single vertex, and then every single iteration, we're removing exactly one vertex from U. So it starts with every single vertex, followed by one fewer, followed by one fewer, followed by, in general, n minus I vertices. So that's one bit of useful information. And now let us look at this code here. Well, what are we doing? V sub j is the edge we are adding. So maybe we would want to look at how does this depend on V sub j. As we saw in our graph algorithms section, we're looping over every edge incident on Vj. Therefore, the pink code, the lavender code, sorry, the body of the for loop on line 12 runs degree of v sub j times. So that checks in that for loop, it runs degree of v sub j times. What is the cost of each run? Well, looking at it, we just check whether or not v sub k is in u, and we also check whether or not the weight is less than or equal to the cost that we currently had. If it is, well, then we update the cost to be that weight. So this is exactly what we were doing, where we're always updating to find the best current thing. This parent variable here corresponds to the best we found so far. In our example up here, that was these light gray arrows I was drawing. Now, with all of this, well, we're going to analyze the dark green stuff as the sum from I equals 0 to n minus 1 of n minus I. That is an arithmetic sum. Again, it's just adding up n plus n minus 1 plus n minus 2 all the way down. You could write it out if you wanted, but this is going to be n times n plus 1 all over 2. And maybe we'd need a constant somewhere and a constant somewhere to make this formal. And now, the body of the for loop here runs degree of v sub j times, and it runs for every single vertex if we're adding every single vertex to the minimum spanning tree. Therefore, the runtime of the lavender code is the sum from j equals 1 to the number of vertices of the degree of v sub j. And hey, we've seen that a bunch of times by now on the graph algorithms section. That has a runtime of 2m. So we have 2m for this part, and we have n squared for the other part. Therefore, the complexity here is going to be theta of n squared plus m, which is not necessarily ideal, but is thankfully better than what we saw before, because in our previous case, our lower bound was n squared, and that was based on this fact that we had n times m. So this is a better runtime. We achieve that by adding a bit more storage. We add 2n storage, because we're storing costs and parents now at each vertex. So by adding in that additional storage, we gain some runtime benefits for this code. There's a couple of things that you might be asking, like how can I easily determine whether or not something is within a set? Those are questions that we may address later with something like union find, or you could also store these things potentially in a hash table or some other data structure to do that in constant time. But we are not going to contend with that particular detail here. So this is a more efficient algorithm with this runtime as opposed to theta of n times m. And it's also less easy to make mistakes here because of the fact that we are doing more bookkeeping. So when running by hand, this is typically the algorithm I will use. The question remains, can we do better than this? And the answer will be yes, and we'll do that by using data structures that are more sophisticated than just storing stuff at the vertices. So that will be our next algorithm that we get to look at.